Hi everyone, this is going to be a video walkthrough of problem 8 on CS61B Spring 2021 Midterm 2. So before I start, a quick preface. I think this problem is really challenging, but I also think it's really valuable to try it on your own before watching this video. So if you haven't given this problem the justice it deserves, pause the video, try reading through this problem, try solving it on your own. If you're still stumped, then you can come back and watch this recording, or if you even just want an alternative view of how you could approach a problem like this. So without further ado, let's dive in. In this problem, you will write code that performs a split operation, as shown in the diagram below. So we have some split operation. It works like so, but we'll get into that after we go through this description. So the split operation recursively splits every node x in the tree into two nodes of half the value, which we will call XL and XR. XL keeps the left child of X, and XR keeps the right child of X. In place of the node which is actually split, a new node is created containing 0. So let's walk through this process, and I've copied this same example up above. Okay, so what we're doing here is we're going to perform split of 6. And this is going to be the new tree after we perform split of 6. So when we perform a split of 6, the first thing that it tells us to do is take this 6, okay, we'll take the 6 and split it into two threes, which are connected to where 6 was before, and 6's spot is filled with a 0. Okay, that's the first step. The second step is what we're going to do is look at 6's children and partition them into two groups. Okay, we're going to have the left subtree and the right subtree. So we will call this the left subtree rooted at 6, and we will call this the right subtree rooted at 6. Okay, so now what's going to happen is after we have this 6 node and we break it up into two threes, the next question to ask is, what are the children of these two threes, right? So the children of the left three is going to be us splitting the left subtree, okay? In the same light, the children of the right three are going to be us splitting the right subtree. So let's walk through the left subtree first, okay? So looking at this left subtree, the first thing that we're going to do is take the root of the left subtree 14, and we're going to break it up into two nodes of equal value, 7. So again, we're going to further partition. Looking at 14, we're going to break it up into the left and right subtree of 14. So we can see this is the right subtree of 14. This is the left subtree of 14. So let's do the left one first, consistent with, I don't know, how we've been doing things so far. So looking at the left subtree of 14, we know that's going to go right here under the left 7. Okay, so what we're going to do is we're going to take this 7 and split it up into a 4, or we're going to take the 8 and split it up into two 4s, right? So we've done that. Now what we're going to do is the following. We're going to look at this left subtree of 8, which is nothing, and we'll look at the right subtree of 8, which is 10. Okay, so we see that there's a 10 on the right subtree. What that means is we go to the right 4, and then we put the split 10. Okay, so now we've successfully finished this left subtree. Let's just put a quick check. Let's move to the right subtree. So after going to the right subtree, the first thing that we're going to do is take the root of the right subtree and split it up into two nodes, right? Both value 8. Then we will repeat the same process. We will take the 16 and we will partition it into the right subtree and the left subtree. Okay, What we will notice is the left subtree is empty, which means that the left 8 isn't going to have any children. We're going to look at the right 8 here, and we will notice that the right 8 has children. More specifically, the children of this right 8 is this subtree when we've split it, okay? So let's take the root of this subtree 10. We will split 10 into 5 and 5. The next thing that we're going to do is further partition into the left subtree at 10 and the right subtree at 10. And then what we'll realize is that this left subtree is going to go under the left 5. So we can quickly add the 2 split into 1 and 1. In the similar light, we will take 30 and put that under the right subtree into 2 15s. So this is the split operation. And one thing I want to emphasize is even after walking through this example, if we're still kind of iffy on like, how does this work? That's totally okay. The first part of this problem is for us to build intuition, and then we'll figure out how to translate that into recursive code. So after walking through this example, we're still confused, perfectly okay, even normal. And we'll walk through some more problems to gain intuition. Okay, so that's how split works. And let's move on to part A. Okay. As a warm-up to parts B and C, if we called split on the node denoted as P in the figure below, what would be the resulting subtree? Assume that our tree stores integers and then Java rounds down. For example, 11 divided by 2 is 5. And they tell us we'll get more out of this exercise if we try to do it first without looking at the multiple choice answers. Okay, so give me a second to quickly charge my iPad. The 4% is giving me anxiety. Nice. Anyways, diving into this problem, let's take this tree and let's walk through the process of splitting 20. It's going to be the same thing we did before. I'm just doing it for part A. Okay, I'll go a bit faster than I did before just because we've seen the process of splitting once. So what we're going to do is we're going to create the new tree. Okay, and we will label this the new tree. And when I say new, I'm going to put that in like, I don't know, quotations. It's not actually a new tree. It's just the modified tree. So actually, let's just change that to modified. That's a better way of saying it. So we have this modified tree here. Okay. So the first thing that we want to do is in this modified tree, we want to take the thing that we're splitting and replace it with a 0. And now what we're going to do is decompose all of the children of 20 into the right subtree and the left subtree. So looking at this left subtree, let's explore there first. We're going to take the root of the left subtree, split it into 2 parts, and put that under the left 10. Right? And where did I get this 10? That's when we split 20 into 2 10s. Okay? So now let's move on to this right subtree. We'll take the root of the right subtree and put it under the right 10, like so. Then what we're going to do is take this left subtree and right subtree of the second 4, and we'll recognize that the left 2 is going to contain the left subtree split. So this will contain 2 5s, and the reason we get a 5 here is because 11 mod 5, or silly me, 11 mod divided by 2 gives us 5, which is, I think, exactly what this for example tells us, which is pretty cool. How did they know? Anyways, so, and we can see that when we look at this right 2, the children of the right 2 are going to be us splitting the right child of 4, which is 11, which also gives us 2 5s. So looking at this tree, we'll see that this corresponds to answer choice 1. Okay, so I already had that bubbled in from before, but we will bubble that in once more. This is the exact same as this. So moving on, Let's move on to part B. As noted above, the split operation recursively, very important, recursively splits every node x in the tree into two nodes of half the value, which we will call xl and xr. xl keeps the left child of x and xr keeps the right child of x. We call the tree rooted at xl the left split, and we call the tree rooted at xr the right split. Write the functions split left node p and split right node p below. These should return the root of the left split and the root of the right split respectively. For example, consider the output of split left and split right on the node denoted as p below. So looking at this example, let's try to understand how split left works. And then once we understand like the details of split left, let's try to connect it back to the larger problem of split that we tackled in part A and in the example. So split left, what it does, we take some node p, we're going to half its value to 20, and then we're going to recurse and kind of perform split on that left subtree as so. And then split right does that same process just on the right subtree, okay? So that's how split left and split right work. I think in this example it's a bit confusing, so let's kind of go back to what we're more familiar with, which is this first example over here. This is the same example I talked about in this instance, is that when we're calling split of 6, what we're going to do is split it into the right subtree and this left subtree, right? So in order to get this left subtree, this comes from split left of 6. Okay, and then this right subtree comes from split right of 6. So how did I like jump to this conclusion, you might ask? Well, I kind of mentioned that in this problem that we read. It said here that we call the XL, the tree rooted XL, the left split, and we call the tree rooted XR the right split. So we can kind of see that the left split should come from split left, and this right split should come from split right. Okay, so looking here, we can kind of see that when we call split left on 6, what we expect is this green tree to be returned. In the same light, when we call split right on 6, we expect this red tree to be returned. Okay? Now that we kind of understand how split left and split right work, let's dive through the skeleton code to gain a bit more intuition before actually writing any code. So looking at this skeleton code, what we can see here is that we have some node class, which makes sense. We're creating a tree, we should probably have access to the node class. And it specifies your split left and split right methods should not modify the tree passed to them. Instead, they should generate an entirely new tree. You cannot use the split node p method in these methods, okay? So I'm going to approach this as a student, and I think it's valuable just to like see my intuition on how I approach the problem, okay? So the first thing I notice is that the code provided for split left and split right is identical, which makes sense because split left and split right are symmetric processes. Split left works on the left subtree, split right works on the right subtree, right? So for now, let's just ignore all of this. Okay, let's first worry about split left, and then once we get split left working, I think since split right is a symmetric process, it should be pretty similar or simple just to like tweak the code for split left. Okay, so looking at split left, let's kind of decompose the skeleton code provided. The first thing we'll notice is we have some sort of base case. Okay, the next thing we notice is that we're given a line here to create a new node. So why are we creating a new node? It's because the problem states we should generate an entirely new tree. Okay, so I'm guessing this new node is going to be the root of the split left subtree, right? So if we're creating a new node, it probably implies that we should be returning that new node since the split left return value is node. So I'm just going to go ahead and add in this line return new node. We don't know where it's going to go in this function, but we know it should exist in this function, and a good default place to put it is at the end. Okay, so we can kind of see here, we have the base case. We have this line which creates a new node. The last thing we need is to assign left and right children. And we should probably also have some sort of recursion, right? So my guess here is this is where the recursion is going to go. And we probably will have two recursive calls. We will have a recursive call to create like the left subtree for the new node, or create the left child of the new node. And we will have a recursive call to create the right child of new node, right? So looking at the skeleton code, let's go back to the problem and see how we can kind of adapt this skeleton code for the problem, okay? So going back to this example, what we will notice is that after calling split left on 6, we want to return this subtree, which implies that we want to return a new node. I'm going to change the color of this just to highlight it. Okay, so this is going to be new node, right? Because in the problem skeleton code, we decided the new node is going to be the root of the split left subtree. In this case, we see that new node is going to be 3. So new node is probably going to be half the value of p. Okay, so now next step is really important. So we've created a new node which has half the value. So what are the left and right children of new node? Well, looking at new node, the left and right children are both 7. So what this means is that when we execute split left, we ignore the entire right subtree. This is very important. Since the left and right children of new node are both 7, it means that they both got the 7 from this 14 node, which means that we're completely ignoring this right subtree, right? So we've decided that the best way of creating this left and right subtree is probably using recursion. So how did we decide that? Well, the problem kind of like implies that we use recursion. So my idea is when we're assigning new node.left and new node.right, we're probably going to say new node.left is going to be the value of some recursive call. New node.right will also be the value of some recursive call. Well, what recursive call? So what we know now is that looking at new node.left, we will realize that it corresponds to us splitting the left subtree at 14, right? That's what new node.left corresponds to. In a similar fashion, new node.right corresponds to us splitting the subtree at 14 to the right. Okay, that's really important here. So both recursive calls are going to be on 14. So we know that new node.left will be the result of some recursive call on 14. New node.right will also be the result of some recursive call to 14. But what's very important here is that these two subtrees are different, which means that we're probably going to have different recursive calls, but both are to the same node 14. So the only way that we can have different recursive calls to the same node is if the function that we're recursing on 14 is different, okay? So this is kind of the final crux of the problem, is that if we notice that this left subtree for a new node is simply us calling split left on 14, we can see that this is just split left of 14, right? in a symmetric light, we can kind of see that this right subtree is just us calling split right on 14. And if it's hard for you all to see that, we can honestly get to this just by guessing. And the reason we can get to this by guessing, it sounds bad, but in an exam, you may not have the time to prove it to yourself. Intuitively, we know that if we're looking at this node 3, and if its left and right children are both 7, it means we're issuing some recursive call to 14 in both cases. But since these trees are different, it means that the recursive call must be different. And the only way to have a recursive call that's different when both of these recursive calls take in the same parameters is if the function itself is different. And the only other function we have at our disposal is split right. So we can just get to it by guessing, but I think it is good to understand why indeed this isn't the case. And just to reiterate that once more, when we're looking at the left subtree of this 3 node, it's going to be us calling split left on 14, just because that's the definition of this recursive process. Okay, well, let's kind of apply all of this code that we talked about to this problem, and we're basically at the point to be done with these few lines right here. So the first thing that I'm going to do is create new node, and our specification for new node, and in that example, was we want new node to be half the value. So let's say new node is p.value divided by 2, and then we're going to set the left and right child to null because we decided to assign the left and right child on the line below. So the new node.left is going to be us calling split left on p.left. And this is what we mentioned from the previous example. I'm just kind of generalizing the call from above, right? Split left on 14, well, 14 is p.left. So that corresponds into new node.left is equal to split left on p.left. Symmetrically, we can see that this other side should be split right. This is important on p.left because both the right and left subtrees both start from p.left. Okay, so the last thing here is we need to figure out this base case. So a good generic base case when we approach these type of tree problems is if p is equal to null, let's return null. So my question is, does this actually work for this problem? And we can kind of see by walking through an example. Suppose that p passed in is the node 10, and let's suppose that p doesn't have any children. What our expected behavior should be after calling split left on p is that we should return the new node 5, right? Well, let's see if this base case actually creates such a behavior. So after calling split left on p, we will ask ourselves, is p null? No, it's not. So what we do is we create a new node of value 5. Then we're going to say new node.left is equal to split left on p.left. Well, p.left is null, so calling split left on p.left will give us null. So 5's left child is null, same with its right child, and we see that this base case indeed gives us the expected behavior. Okay, so with that in mind, let's kind of move to how can we replicate this same logic in split right. Okay, so what I'm going to do is in the beginning, we kind of told ourselves that split right is basically the same exact thing. The only difference now is that instead of looking at p.left, now we're going to be looking at p.right for those initial recursive calls. And I'll explain why this is the case, but the only change we actually have to make is changing this to p.right. Okay, so let's see once more why this is the case. Well, let's kind of get rid of some of this. Okay, so when we call split right on 6, all we're doing is that In the symmetric process of split left, when we look at the left subtree, now in split right, we only look at the right subtree and we ignore this left subtree when we call split right. So what that means is that the recursive calls should both be on p dot right. We should have one recursive call that generates this right subtree, which will be split right on p dot right. And then we should also call split left on p dot right to generate this tree right here. Okay? And that's indeed what's happening with this code. Okay? Let's quickly add in the semicolons that I neglected, and that's going to be the solution for split left and split right. Okay, we're almost done. All we have to do now is write the split node p method. This method should modify the tree that it is given. For example, if we call split p, where p is the node containing 6 in the figure at the top of this page, after the call is complete, p.value should be 0, p.left.value, and p.right.value should be 3, etc. Also assume that p passed in is never null. So in order to complete split, we can use split left and split right, and let's just walk through this example to see how we can do so. Okay, so we see that when we call split left and split right, we create the respective subtrees. Okay, these are the results after calling split left and split right on 6. Oh my gosh, I'm just writing over this now. So this is after we call split left of 6, we get this left subtree, and after calling split right, we get this right subtree. So my idea here is, what if we set p dot left to be split left on 6, we set p dot right to be split right on p dot right, and then we can simply change the value of p to be 0. Okay, so we can add that in quickly. So we'll say p dot left is going to equal to split left of p dot right is going to equal to split right on p. And then after executing these operations, it's very important, now we can set p's value equal to 0. If we had this before, the problem is that after split left looks at the value of p and it would see that the value is 0, and then we kind of messed up setting the value of the first node, right? Just kind of reiterating that in this example. Suppose that we set this value to 0, and then we call split left on 6, or on p. What's going to happen in this case is that this value would be 0 because we take p's value and we divide it by 2 in the new node, right? So we can see that we need to execute p dot value equals 0 after we do split left and split right. Okay, so that's all for this video walkthrough. I hope you guys found it helpful, and have a good rest of the day.